In this lab, we are going to configure BGP in the topology, which you can see in GNS3. Everything is pre-configured besides AS65001. The BGP peering and everything else is already set up in the other autonomous systems. So we won't touch these in this lab. In AS65001, I have already assigned the IP addresses and set up the IGP, which is OSPF in this case. And here is the routing table. On top of that, we are going to configure eBGP between the routers in the autonomous systems 65001 and eBGP between the different autonomous systems. The goal of this basic lab is that we should be able to ping the loopback interfaces of every other router in the different ASs, which should be advertised with BGP. And just to keep the BGP table simple and short, every other router advertises only its own loopback address with the /32-bit mask. And we will do the same in AS65001. So let's start with router 1. As I mentioned, we have full connectivity within the autonomous system thanks to OSPF, but we don't have connection to the outside. So router 1 can ping every other router in its own autonomous system. So R3, for example, but can't reach anything outside the AS65001. First, we are going to set up the eBGP peering with router 4, and I'm gonna start packet capture in the background. So in global configuration mode on router 1, router BGP 65001, and this is the AS number. And because we use IPv4 unicast addresses, we don't need to define an address family because it's usually the default. So we only need one neighbor comment here, then 014.4, which is our force address on G0/0, and the remote autonomous system is 65,004. And because I have already configured everything on router 4, the eBGP neighbor relationship has been established. So we are ready to exchange routes. But let's see what happened in the background. BGP works very differently than other interior gateway protocols. First of all, we don't use multicast addresses and dynamic discovery, but we explicitly define the neighbor addresses, and we use TCP to establish the BGP session between the peers. So we have the usual three-way handshake, SYN/SYN/ACK, and the destination port, which BGP uses, is 179. So we have a TCP session established between TCP port 179 and 43,000 something, which is just a random port the client has chosen. And R1 is listening on TCP port 179 and waiting for the incoming SYN packets. And by default, if we set up eBGP, so BGP between different autonomous systems, the TTL value in the IP header is set to 1, so the two routers must be directly connected, otherwise they won't become neighbors. We can modify the TTL with the eBGP multi-hop feature, but usually the eBGP peers are directly connected. This works differently with iBGP, but we will talk about that later. And as we can see, we have already exchanged routes with router 4. This NLRI, which is network layer reachability information, defines the prefixes which we are advertising and the corresponding path attributes, the AS path, origin type, and next hop, and so on. These are mandatory transitive attributes, so they have to be included in every update message. For example, the AS path, we have to go through these autonomous systems to reach 777, which is router 7. We can't use this link between router 2 and router 7 because the eBGP peering has not been configured on this link yet. Every eBGP router changes this next hop address to its own address. This 10.0.14.4 is router 4's address. This works very differently between iBGP peers, so they don't change this next hop address by default, which can cause issues, but we will address this situation later. And the origin code, which is IGP, which means that we have used the network command to advertise this 777 address on router 7. We can also use the redistribute command. In that case, this origin type is called incomplete, but we will talk about these path attributes in a different video. So router 1 received these routes and they get into the BGP table. So show IP BGP. These are the networks router 1 received via BGP, but only the best routes get into the routing table if the next hop address is reachable. So let's check the routing table, show IP route. And indeed, we learned the new BGP routes, eBGP routes to be exact, because the administrative distance is 20. The AD of an iBGP route would be 200. So let's try to ping router 7's loopback address using our own loopback address as the source IP address, and it fails because router 7 doesn't know R1's loopback address. So let's advertise R1's loopback address with BGP. By default, we are not advertising anything in contrast to OSPF and other IGPs. We have to do everything manually. We have two options if we want to advertise networks. We can either redistribute other routes into BGP, or we can issue individual network statements, and this time we will use this second method. So network 1.1.1.1 mask, and we have to exactly define the network mask. In this case, it's a /32-bit mask. So it's 255.255.255.255. We can only advertise routes which are in the routing table with the same network mask as in the routing table. Now let's check the other routers if they receive this 111 route. So router 7, for example, show IP BGP, and it got this route. Remember that we haven't set up iBGP peering within the AS65001, so router 1 can't pass this NLRI to router 2 or router 3. The information about this 111 network goes through this path, and AS65007 gets this information from AS65006. By default, eBGP peers forward this information to other eBGP peers. So this NRRI eventually reaches router 7. We can see that we have to go through these ASs. So AS65006, AS65005, and so on to reach 65001, because we can take this path between router 2 and router 7 just yet. And this I letter at the end of the AS path string indicates that we have used the network command on router 1 when we advertised this route. If we used the redistribute command, we would have a question mark here, meaning that the route is incomplete. We prefer I, so the network statement, to incomplete if we have a tie in the AS path length. Now router 7 received this route, and it should get into its routing table according to the greater than sign here. So show IP route 111. Now we should be able to ping R7 from router 1. So do ping 777, source loopback 0, and the ping is successful.